Good afternoon, everyone. Well, first of all, I will talk about some topics. I will tell you what are the topics that I will talk in this day. First introduction about me, some definitions that will be really useful for the explanation of the methods that we are developing. That is chem.cr, an overview, some features, benchmark, and multiverse. This is a conformer generation. I will go deeper in this in the talk. And femdoc, this is an algorithm for molecular docking. So those two algorithms are applications of chem.cr. So, and at the end, I will talk about my experience using Crystal language. Well, about me, I am a chemical pharmacist. I am not an informatic or programmer, right? I did my studies in Colombia. Then I did a PhD in applied science in Universidad de Talca in Chile. I focus mainly in the study of proteins and the behavior of proteins, how the drugs interact with the proteins. I started a postdoc in 2019. And now I am an academic researcher of the Universidad Católica del Maule. I belong to the LavinMQ, that is the Laboratorio de Química Computacional, de Bioinformática y Química Computacional, and I belong to the CIAM. This is the Centro de Investigación de Estudios Avanzados del Maule. Well, first of all, what is computational chemistry? A really short definition is that the computational chemistry is a branch of chemistry that uses computer simulations to study some properties, behavior of molecules and materials in overall. And another really important concept in the computational chemistry is what is a molecule. A molecule is the most simplest unit of a chemical substance, right? One molecule is defined as the binding of two or more atoms that are covalently bonded. And a protein is a molecule also, but it's larger. It's a large complex molecule that is made for one or more chains, and this is composed by amino acids, right? And the amino acids are binding by peptide bonds. And some examples are the enzymes, the hormones, the antibodies. So you can see in this scheme, one amino acid, another amino acid at the peptide bond, and the difference in the sequence of a protein is the R1 and R2 amino acids. So you can have this arrangement of units to form a protein, and the different proteins are composed with different amino acids and different lengths. So you can see here at the left a typical drug, and to the right a protein. And you can see the same drug just in these small spaces, just to see a magnitude of the size. But this protein is composed with a lot of atoms. So the protein, this is a simplex protein. There are really complex protein and really big, and treat with this data is really difficult. So for this, to treat this data, exists a lot of formats, right? There are a ton of file formats for encoding this chemical structure, but this is really difficult because those formats are different, and often there is no transferability between the software. So for instance, a PDB structure, you can see here some header, some numbers that codify every atom in the structure, the name of the atoms, the name of the residue or the molecule, the chain, the residue, a lot of information, the X, Y, and zeta coordinates. This is really important for us, the coordinates. And then you have another columns with some experimental information. But exists a lot of different formats. This is PDB, one of the most widely used, but you have also a mol format. You have the coordinates in these columns, but there are another fields in this format. And mol2, you have also the coordinates, but other properties this partial charge. So when you read these files, you need to add some information to enrich the information of this data to treat and to use with another specialized software. So and that's why born chem.cr. chem.cr is a modern library written in Crystal language, right? And it's useful for the manipulation, the analysis of these computational chemistry files. chem.cr is been developed by Francisco Adasme. I have done some small contributions and mainly tested the coding and raising usage, but the main developer is Francisco. And I will talk about why chem.cr, what is the motivation behind the development of chem.cr in Crystal language. So there are another similar software. For instance, ChemFiles is a library also for reading and writing chemistry files, but it's written in C++, and you can also and you can also use Python, but it's mainly focused in simulation trajectories, right? And this does not provide an object-oriented topology access, and this is really important. And I will talk to you a little more about this. OpenBabel is another massive library written in C++ and support more than 110 formats, but the app is really complex to use. And a lot of other libraries are written mainly in Python, and this usually means two things. The first one is this is no type safety, right? So sometimes it's really difficult to use if there is not enough documentation. And this is really common in this specialized software. And second, one must to deal with the C performance if you want to develop something really specific. So this is really difficult for scientists and mainly for people like me who doesn't program, right? So it's difficult to develop a new specific protocol or algorithm. So another two libraries of software is BMD and Schrödinger. They provide API for TCL and Python also. However, they suffer from poor documentation also. So chem.cr, I will talk about some features. First, the structure reader. For now, chem.cr supports those structure formats. Really important, one of the most commonly used. And you can use it in this way: require chem, include chem. And you can create an object structure, use a structure, create an object to read the file, and also you can select which chains, which kind of atoms to load from the beginning. And this is important because some models are really heavy and require so much size. The hierarchical object-oriented access to molecular structures is really important because in chem.cr was developed following a programmatically way to select the parts of the structure that you are interested for. For instance, you can select the chain A, right? The amino acid number 10 and the carbon alpha, the CR carbon. And you can do it in this way or using the method dig, and you can and this return another object, and you can access to all the properties of this object. This is really different in another language and another libraries because, for instance, in MD analysis, another really famous and really used library, you make the selection with this method and a text selection, and this is not really safe, right? About the topology properties, yes, you can access to a lot of properties like the name, the coordinates, like the occupancy, and the molecular mass, the charge, a lot of information that is enriched by chem.cr in the structure. So this is really cool because this lack in a lot of formats. The atom data is simply defined as properties of the atom class. So it's a class in all the properties are really well defined. So in most of the other libraries, you get an array, and you need to iterate in the array to get the property that you want, and this is also not safe. You can do also special measurements, right? You can select two atoms of the structure and calculate the distance between those atoms, calculate the center, this return a vector, calculate the RMSD, the root mean square deviation, the radius of gyration, any other spatial measurements. And the good thing is that all these calculations are implemented in pure Crystal. This doesn't use C. So about the scientific production, using chem.cr, a first article was published in 2019. I don't know if it is the first scientific article using Crystal that was published or not, but this was published by my friend and colleague Francisco and his psych, and uses Crystal in a really prestigious journal. This is the Journal of Chemical Information and Modeling. So about the benchmark, here you can see three examples, three proteins, one protein with just a few atoms, 327, another protein with a little bigger, right? And another model that contains 10 models of this size. So this is way bigger. So the benchmark, you can see milliseconds and seconds. chem.cr is the fastest between BioPython, ChemFiles, MD Analysis, MD-Track, Schrödinger, and BMD. Schrödinger is a paid software. BMD is open. And you can see that only in this model is faster BMD. But BMD lack of some of the functions like parse header, every 36, hierarchical parsing, support disorder because the protein has several alternative conformations in some of the amino acids. And so with taking all this in account, chem.cr is leading in this moment. Well, so taking chem.cr, we started to work in develop some other protocols, some other algorithms, and I will talk about multiverse. Multiverse is I have to say, you can see here a molecule. A molecule can have a lot of different conformations when they are free in the water, right? But when they go into the binding site of a protein, they adopt some really specific conformations. And some of those conformations are really useful for you to predict another properties. For instance, if you know what are the conformations that a molecule adopts before to go to a protein, it's easier to find the shape of other proteins. And so it's a really good information, but it's difficult to obtain. So the multiverse, we try to generate conformers. It's a kind of conformations of the molecular in the low energy conformational space. This means that some conformation really stable. And usually you measure this with the accuracy as measuring the root mean square deviation between the atomic positions of all the conformers. If they are really close, it's the same conformation, right? So also another critical step is the ensemble size, because often you need to search in a big database of millions of proteins. You need to test a lot of million molecules. So you must generate the minimum ensemble conformation that represents better the conformational space of a molecule. So another critical step is the computing time, right? Faster usually is better. And so the conformation generation is a well-studied problem. So what we are studying this, right? Some people solved this problem a long time ago in 2017, but not at all, because when you start to work with bigger molecules, it's really most difficult to predict the conformations of the molecules. So we wonder if enhanced sampling methods could help to solve this problem. This kind of method is a kind of molecular simulation. It's a really complex method in which you applied a kind of potential to force the molecule to have different states. So I won't go in detail about this method, but I will show you what we obtained. So we took CADD and ConForge. ConForge was published like 1.5 months ago. It's a new method. And CADD is a well-established open source software. And we test one molecule that is called FAT. And it's not unusually a small molecule. It's a bigger molecule. It's not the typical drug-like molecules. We took 2,371 PDB structures of the same molecule in the database that were obtained experimentally in several proteins. And so we took these structures and we started to generate conformations of this molecule, and we started to compare if we could predict the conformations. So we got this. In ConForge, you have these distributions. The RMSD is how similar was our ensemble against every molecule in the database. If you have smaller values, you have a more precise prediction. So you can see ConForge in this part. And well, often 2 RMSD is a cutoff, and 2/2 tells you that you predicted the structure with a good accuracy. And so here you can see ConForge, and the extreme value was 3 angstroms, a little far away from 2, right? Then you have CADD. It has a really good prediction in this area over 2, but one molecule was predicted in 4.3, really far away. And we have a multiverse, our version, 2.9, and with this distribution. Usually you can see also this in a threshold. And you can see in this part, the important part, with ConForge, 14% was predicted, 71 with CADD, and 81 with our development. And you go to the next step, almost all the molecules were predicted over 2.5 RMSD threshold. So this is a really interesting result. And we are working with more molecules, and probably we will publish this soon, because this is a really good prediction. Those are one of the top lead methods. And so this is one of the applications. The other application is FEMDoc. We are developing a new docking algorithm that is called free energy mass-based docking algorithm. So we're trying to calculate. We did this protocol. We prepare the protein, we parameterize the ligand, we generate some grids, and we perform a conformer generation using multiverse, of course. And we also, at the end, we test all these conformations in the binding site of different proteins, just to try to find the best molecule in this protein. So we generate these 3-dimensional maps. This is the potential energy, the electrostatical energized potential. It's a kind of interaction maps. And then we use these maps to test all the molecules inside them. So for instance, here we work with a protein, the HAB1 protease. We selected different molecules with different affinity values, and we obtain RMSDs in this purple line, and we compare against Glide. This is a commercial software. We obtain, even in some cases, for some molecules, lower RMSD values. So we are getting a really good prediction. but one system is not really significant. So we test this really early development in a data set of 200 protein complexes, and we are here. Sendog is in the half of a lot of other energy functions and methods, and those methods in this top part they exist around 15 and 20 years ago. So now we are in the middle, and we want to go higher. That's where we are putting a lot of effort in calculate these free energy maps. So last, I will give you some comments about my experience using Crystal. The positive is the transition is easy. I worked a little with Python, and I did the transition, and it feels really, really easy, the transition. The statically type and time inference is really safe and useful, especially for me. The source document code is really useful. I did this only reading the documentation and the code. The ECR module is extremely useful because we work with another specialized software that they talk the value, the key and a value, right? And you need to give these configuration files to this software to perform the calculation. So we generate these files using ICR, and it's really easy to do. To improve, I think more examples. Nibus, like me, we learn from examples, and the examples is a good source of information and knowledge. So this would be really cool. So last, I want to acknowledge to some collaborator, Hans, Francisco Adame, the developer of chem.cr, and Leandro Martinez. Yes, you have the chem.cr code here, and multiverse. I released multiverse tonight. It's really, really, really messy, the code, but I want to invite you to collaborate, and I promise when we publish the work, I will add your names in the anonymous part section of the published paper. And so it's an invitation for everyone to collaborate. You will see that it's really messy. I didn't use macros. I wrote everything as I understand. And so a good help will be really fine. So thanks.
Okay. Do we have questions? I do have one, but I don't want to. I have a little one. In one of the earlier slides, you showed the types helping you, right, with the structure of the thing. Can you go back to that?
Yeah.
Yeah, here is enough. While you were mentioning this, I was thinking, so this structure of having a char first, an integer, and then a string, this is coded somewhere, right? It's part of the file specification, or what?
No. Oh, yes, in the initial format, for instance, in the PDB, you have let me see. Yeah, you have here the atom numbers, the index, the name of the atoms, and then you have a name for every different molecules in this model. And in this based on this, in this name, in this chain, and in this number that is the residue also, you start to break all the molecules of the system. So you need to start to organize based on those columns, the information.
But what I mean is, you know that the first component will be an integer, like 1, 2, 3 there. The second one is going to be a string, C1, C2, right? Or not? Or I'm mistaken?
Yeah, this format is really is really hard, because it has a specific width of every column. It's a well-established format, but it's really limited. Yeah, because when you have bigger numbers, what you do, right?
Right. So you're basically admitting any value and then just using the specific one when you need it.
Yeah. Inside the library, there are a lot of ECR templates that evaluate these files, start to test in the templates, and start to assign what is the format, for instance.
Yeah.
Yeah.
Okay, there are no more questions, I think, in the forum, in the room.
Fantastic talk.
Thanks.
My question would be, I think Crystal has enormous potential for this kind of applications, but I also think Python has a huge network effect and an incredible amount of libraries. I always thought that's why we couldn't really get traction there. So, but you went ahead and used it, and now you're happy with it, right? So my question would be totally uninterested. How would you do to attract more of your colleagues to using Crystal on these sorts of applications?
Yes. In this moment, we are starting to develop these new algorithms and others that they are not here. And these algorithms, we will implement some short functions that will be generic for another protocols. For instance, if you want to take one molecule and you want to simulate the molecule in water for any specific time, just to calculate some properties of this molecule. And so if you do this manually using the specialized software, it requires a lot of time. You need to invest hours trying to load the files, convert, and dealing with the formats. And so we want to create some specific functions just to do this automatically. And so with this in mind, I think that the people will be really happy to have these short functions to do every task that is hard to do, right? And so I think for using these strategies, we can attract people and attract people who is interested also for developing new protocols, because the Crystal language is really natural, and it feels really. For me, it's really natural to try to put this protocol that are easy, just some instructions in a specific order, dealing with the formats, and it's so natural and it's really different to others. And it's really similar to Python in that sense, but in Python you miss the type safety and other things. And so I think the strategy will be this. And also developing these new methods, the people will be interested, especially in this field, because they are working. Now we are getting really nice results. So this, I think, will be really useful for all the community, for all. Yeah. Thanks.
All right. Thank you.